Welcome back to Calculus 2, Section 3.6, Numerical Integration. So we have quite a few topics to go over. We're going to get started with the midpoint rule. Let's get started. Here we are looking at a graph of a function f of x, and a portion beneath the graph has been shaded. Recall that in building the definite integral, we looked at approximating the area using rectangles, where heights of the rectangles, in this case, are produced by looking at left endpoints. Equally, we could use right endpoints to produce heights of the rectangles. Here, we're introducing the notion of the midpoint rule, which is to use midpoints. Let's take a close look. We have three rectangles with identical bases. Each base occurs over a subinterval, which partitions the interval a to b into three equal subintervals. Each subinterval we've marked with a little blue dot the midpoint of the subinterval. And above each dot, we have found the height of the rectangle. Let's think about how to compute each of these midpoints, m sub I. We can first note that the length of the entire interval is b minus a, that our notation for the width of each subinterval is delta x, computed as b minus a over the number of subintervals we desire, n. If we want to start at the leftmost endpoint and move to the very first midpoint, we add in half of delta x. Moving from the first midpoint to the second midpoint is one full copy of delta x. Let's look at a way to express that. The ith midpoint, m sub I, is a adding in I minus 1/2 that many copies of delta x. Very good. Let's write down the formal statement for the midpoint rule. We take a function f, which is continuous on the interval a to b. We let n be a positive integer, and we set delta x to b minus a over n. If the closed interval a to b is divided into n subintervals, each of length delta x, and m sub I is the midpoint of the ith subinterval, our notation will be capital M sub n for the midpoint rule, set equal to the sum from I equals 1 to n of the area of each rectangle. Heights given by the function evaluated at the midpoint multiplied by the length of the subinterval. This is a nice Riemann sum. Thus, and the function f is continuous, thus taking the limit of these m sub n's, we'll recover the definite integral, i.e., the total area under the curve. Beautiful. That's the midpoint rule. Let's look at an example. Computing m sub 4 to approximate this definite integral. So the area under the curve y equals x squared over the interval 0 to 1. M sub 4 means that we want 4 subintervals. And then what we're doing, this section is called numerical integration. Numerical integration is a fancy term for a way to approximate. Numerical integration is an approximation scheme. What are we approximating? We're approximating this definite integral. We're evaluating the definite integral using numerical methods. We're coming up with an approximation. So our focus is going to be this M sub 4 will give an approximation to the true value, then compare the true value with the approximate value. All right, let's go through it. So we know that the interval is 0 to 1. We can use that to then compute delta x. 1 minus 0, that's the length of the interval. We want M sub 4, therefore we divide this by 4 and get that delta x is 1/4. Starting at the leftmost endpoint, 0 to 1/4, that will be the first subinterval, and produce 3 more subintervals, where the last subinterval ends at the rightmost endpoint. Nice. As we're doing the midpoint rule, we should next figure out the midpoints of these 4 subintervals. So halfway between 0 and 1/4 is 1/8. Adding a quarter to an eighth gives you 3/8, and so forth. Fantastic. Now that we have the midpoints, we know delta x. We next find the heights at each of these midpoints. So f at 1/8 will give you a height value. 1/4 is the width value. That product is the area of the first rectangle. Do that for the next 3 midpoints. Do a computation and produce our approximate value. 21/64 is the value for M sub 4. Going to the second part of the question, we know that we can easily evaluate this definite integral. X squared integrates to x cubed over 3. Evaluated at bounds produces 1/3. So having these values, 1/3 and 21/64, we can take the absolute value of their difference and find that in a decimal approximation, it's approximately 0.0052. A takeaway here is that for very little work, computing M sub 4, we get a decently, quote unquote, good approximation of the true value. Excellent. So here's an assignment for you. Repeat the exercise that we just did to estimate the definite integral from 1 to 2 of the reciprocal function 1/x. Compute M sub 2 to find an approximate value. Compute this out by hand, and then look at the difference of the 2 values that you compute. Nice. So that's the midpoint rule. Let's look at another method of numerical integration, the trapezoidal rule. All right. So we've got a curve sketched in black. The gray area is the true area under the curve from A to B. And then we approximate that true area by looking at the area of a trapezoid. So we'll denote this with T sub 1. We're just using one geometric object. That B minus A is the length of the base. F of A is one of the two heights. F of b is the other height. Then if we take f of a and f of b and we divide it by 2, we get an average of those heights, times the base is the area of this trapezoid. Okay. Let's divide this further. Let's now look at 3 trapezoids and produce a better approximation of the true area. And let's go one by one through these 3 trapezoids. The first trapezoid has the length of the subinterval divided by 2, multiplying the sum of f of a, the height at the left endpoint, plus f of x sub 1, the height at the first right endpoint. Very nice. Let's see what happens in the second trapezoid. What is its area computation? So delta x over 2, it's the same base. And then note that we reuse f at x sub 1 because this second trapezoid shares this height. And then the second trapezoid has a second height, f at x sub 2. And that pattern repeats in the third trapezoid, that we reuse this height, and then add in the very last height, f at b. So you want to see that all interior heights are used exactly twice, and the boundary heights at a and b are only used once. So let's write that out. Here's the precise statement. Let's clear the screen a little bit. Here we go. So the trapezoidal rule, like before, we take f to be continuous, closed interval a to b. We let n be a positive integer. Delta x is defined as before. N subintervals, each of length delta x. And then t sub n, we're always going to have delta x over 2 for the trapezoidal rule. And then that multiplies a sum of heights where all the interior heights get doubled up. Very good. And this is also a Riemann sum, and it recovers the true area under the curve in the limit. Excellent. Now, we have a nice little identity that relates the trapezoidal rule, T sub n, with the left and right endpoint methods. Let's observe how this holds. Let's use some colored dots. Remember that L sub n is you take delta x and you multiply by all of the left endpoint heights. So for each blue dot, just associate that with an f at the input. Multiply that by delta x, and then that's going to give you L sub n. Likewise, R sub n is delta x multiplying all of the heights at the right endpoints. Then these coefficient 2's that appear occur only when you have 2 dots on that height, a blue dot and a red dot. And then at f of x0 and f of xn, you'll have only 1 dot apiece. Thus, that matches the sum form written out. And as L sub n and R sub n do not involve delta x being divided by 2, introducing this 1/2 out in front accounts for this 2 in the formula. In other words, looking at this identity, we see that the trapezoidal rule is the average of the left and right endpoint methods. Excellent. Okay, so quick review assignment for you. Compute T sub 2 for this definite integral. And the second part to the assignment is after you compute t sub 2, go ahead and evaluate the definite integral and find the exact error. Very good. So t sub 2 is a computation using numerical methods. To find the exact error, you evaluate this elementary integral and take a difference of the approximate value and the exact value. Fantastic. We've done the midpoint rule and we've done the trapezoidal rule. And we've talked a little bit already about calculating area. Let's do a few more examples on that. Here we're looking at the parabola function, f of x being x squared. We have three rectangles which are produced using the midpoint rule, and this would be m sub 3. We have an interval from 1 to 2. We can compute the definite integral from 1 to 2 of f of x and compute 7 over 3. That would be the gray shaded area. M sub 3 we can compute is some value. Here it happens to be 251 over 108. And then to find the error in M3 is a value computed using numerical methods, i.e. it is a numerical integration scheme. And the error that it produces would be the difference of these two terms in absolute value. Find that the error is 1 over 108. All right, straightforward. Let's reuse the same function, the same definite integral, but now our approximating functions are not rectangles, but are trapezoids. We still have 3 of them. Compute that t sub 3 is 127 over 54. And then find that the error in t sub 3 is 1 over 54. Note that this is a larger error than m sub 3. Very nice. Okay, so we have explicitly looked at a couple of examples, but there are actually estimates that hold. Let's look at those estimates. All right. So we're going to get estimates for the error in the midpoint rule and an estimate for the error in the trapezoidal rule. Okay, how can we use these estimates? When are they valid? We need for the function to be continuous on the interval. And we need that continuous function to have a second derivative on this interval. Take a look at the bound. The bound on each involves a capital M. That capital M multiplies the length of the interval raised to the power 3. That's the numerator in both cases. In the denominator, there's the number n raised to the power 2 multiplied by a constant. All right, so what is this capital M? This capital M, you want to think of it as a M for max. And capital M is the maximum value of the second derivative under absolutes. And then the maximum value of this function will where we want that second derivative to be looked at everywhere over the given closed interval. All right, let's look at some examples. So let's go back and look real quick. that there is an n appearing in the bounding value. And the example that we're going to look at is asking for us to take advantage of this n appearing in the right-hand side and solve for the n. All right, so let's look at that. So for what integer n, in other words, how fine a partition do we need to take such that the estimate of this definite integral is accurate to within 1/1000th using the midpoint rule? Remember, the midpoint rule is capital M sub n. What value of n should we choose so that the approximation we produce is close to the exact value? Well, remember that that estimate relies on knowing the second derivative. So the first thing we'll do is we'll grab this integrand, f of x being x cubed, take a first and then second derivative of f of x. To compute capital M, we want to consider f double prime over the interval 1 to 2. 6x is an increasing function. So 6x, all its possible values from 1 to 2, the largest value is going to occur at x equaling 2. So capital M, the maximum of the absolute of f double prime over the interval 1 to 2 is 12. 6 times 2. Good. Let's recall what the estimate to the error in m sub n is. It's capital M, which we have already established as 12. B minus a, that's 2 minus 1, or 1 cubed, over 24 times n squared. If we plug in, we know that capital M is 12. That's 12 times 1. 12 over 24 is 1 over 2. Therefore, this quantity simplifies down to 1 over 2 times n squared. And this quantity we want to be smaller than the desired error, 1/1000th. So we take 1 over 2n squared and force that to be less than 1/1000th. So note that there is an unknown that we can solve for, n squared. We can come up with n squared needs to be greater than or equal to 500. The setup of the problem is not to find some condition on n squared, but a condition on n. So we should remove the power 2, and that's easily done by applying a radical. Note that the n value is going to be an integer, and that it needs to be bigger than or equal to this quantity. This quantity is not a perfect square, the radicand 500. So by looking for the smallest integer that satisfies this inequality, we find that it's 23. Nice. Okay, so your turn. Compute M4 and T4 for this definite integral. Compute this definite integral exactly and compare it with M4 and T4. Take the absolute value of their differences and call that the exact error. Good. And then similar to the example that we just worked, for this definite integral with integrand 1 over x, what integer n for the trapezoidal rule t sub n will yield an estimate to within 0.002. So what's the smallest value of n? Excellent. Okay, So we've done the midpoint rule, the trapezoidal rule, and we've talked a little bit about calculating area, where there's this new idea of estimates for the error. We're going to do one more numerical integration rule called Simpson's rule, and we'll also come up with an estimate for the error when using Simpson's rule. First, we're going to establish Simpson's rule. All right, now something curious is going to happen here. Go ahead and draw a nice continuous function, f. Draw its graph. Pick an A, pick a B, shade underneath the curve, and then evenly divide that A to B into 4 equal subintervals. And then come in and draw 2 polynomial functions, a P1 and a P2, where P1 is going to be defined over the first 2 subintervals, and then P2 will be defined over the second pair of subintervals. Okay, so what condition do we want on the P1 and the P2? Well, we want them to be quadratic functions, so parabolas. If they're quadratic functions, then they take the form of ax squared plus bx plus c. Let's focus in on the P1, and let's bring in notation that P1 is defined from x naught out to x2. Let's get rid of p sub 2. Now, the condition that we want on P1, if you look at the red curve of P1, that the red curve and the black curve are agreeing at x naught. That means that the value f at x naught is the same as P1 at x naught. P1 is a quadratic function, therefore it takes the form of a x squared plus bx plus c. This f at x naught is this height value, and this P1 that we've introduced, we want it to agree with f at x naught. So P1 at x naught is a x naught squared plus bx naught plus the constant c. So we're given the function f, and we're trying to find a parabola which fits the graph of f over the interval x naught to x2. Then a parabola needs 3 coefficients, a, b, and c. We've written down 1 restriction, but we can come up with 2 more restrictions, that f at x1 will equal P1 at x1, and that f at x2 will equal P1 at x2. And then this is enough to allow us to determine the a, b, and c. All right. Let's bring in some shading. Let's shade underneath the parabola over the interval x0 to x2. Then that red shading is represented by the definite integral from x0 to x2, integrand P1. And then that is an approximation to the true area under the curve, y equal f of x from x0 to x2. Now the nice thing is that P1 is a quadratic function. It takes the form ax squared plus bx plus c. In this definite integral, we know that we can easily evaluate it. X squared goes to x cubed over 3, x goes to x squared over 2, and c, constant c, picks up variable x. This is a definite integral. We know how to plug in the upper bound and subtract the antiderivative evaluated at the lower bound. All right, let's continue with the algebra. We have a sum of 3 terms. Let's look. We have a coefficient a over 3 multiplying a difference of 2 terms. These 2 terms are each cubes. And we know how to factor a difference of cubes. We come up with a binomial times a trinomial. Likewise, the b over 2 term is coefficient to a difference of squares, and it has a nice factorization. Thanks to this factorization, our sum of 3 terms now have an evident common factor. Factor off the binomial x sub 2 minus x naught. And we will choose to also factor off a 1/6. 2 over 6 is 1/3. 3 over 6 is a half. And 6 over 6 is 1. Good. And continuing with the algebra. Looking at x2 minus x naught, that's going from x2 down to x1, from x1 down to x naught, but from x naught to x1, that's a delta x, and from x1 to x2, that's a delta x. So this difference, x sub 2 minus x naught, is 2 copies of delta x. Okay, that's all that we've done there. We can simplify 2 over 6, get 1/3. Easy peasy. Continuing. Let's do a little bit of rearrangement. Let's look inside the square brackets. Let's start with this 6 copies of C. Notice that we have 4 copies of C plus 1, and then 2 copies of C, yielding back 6C. Let's focus on this 2a next. This 2a gets distributed to this trinomial. We have an x sub 2 quantity squared appears here with coefficient a. We need one more of those to account for all of 2a's. X sub 2 quantity squared. Here's one, and then here's a second one. All right. 2a on this mixed term, x naught x sub 2, appears right here. And then 2 copies of a multiplying x naught quantity squared. Here we have 1 copy, and then here we have the second copy. Okay, so that's all of the 2a terms accounted for, the 6c accounted for. And for 3b, well, gets distributed onto x2. Here's 1 copy, and then 2 more copies. Likewise, here's 1 copy of the x naught term, and then 2 more copies of the x naught term. All right, so we've accounted for all of our terms, and this sum of 2 expressions equals the previous line. All right, well, why would we do that? Well, take a look. This first trinomial is, in fact, f at x2. And the second trinomial is f at x naught. Fantastic. Let's make that substitution for f at x sub 2, and then f at x naught, f at x2, f at x naught. This a on the trinomial, since the mixed term is doubled up, this is a perfect square trinomial. We get binomial x sub 2 plus x naught, quantity squared. And no changes in the remaining terms. All right, so this is kind of beneficial to have an f at x sub 2 and f at x naught. Remember, since we do not know what this polynomial p1 is, we do not know its coefficients a, b, and c. So to rephrase it in terms of the given function f is very beneficial. So left over are these three terms. Let's take a look at where we are. We have the unknown a, the unknown b, the unknown c. Let's focus in on the x sub 2 and x naught. And notice that it's a sum. X sub 2 and x naught, we're taking a sum. So if we're taking x naught and x2 and we're adding them together, if we were to divide that sum in 2, that would produce x1. Fantastic, we'll take advantage of that. We're not dividing by 2, therefore this sum is twice x sub 1. X sub 1 is the midpoint. This sum is twice the midpoint. Very nice. All right, now let's look at the coefficients. We have a 4. We can produce a 4 here. And 2 squared is 4. Aha, very nice. We have a common factor of 4 in these three terms. Factoring off the common factor of 4 leaves us with f at x sub 1, and it will be multiplied by 4. We get 4 copies of f at x1. Fantastic. This is a good result. Let's make a note of it. Let's do a little rearrangement of the terms. I simply brought the 4 at x1 into the middle. And remember that this computation was showing the amount of area underneath the quadratic p sub 1. And then remember that that is an approximation to the true area under the curve from x0 to x2. So then again, from x2 to x4, we can approximate the true area with the area under a curve p sub 2. And following exactly the arguments that we just went through, we can find that that approximation would be delta x over 3. Then f at x4, the ending height, 4 copies of the middle height, and 1 copy of the original height, or the left endpoint height. And now that we have this procedure nailed down, we can partition into any even number of intervals, subintervals that we like. And this is Simpson's rule. So let's write that down, Simpson's rule. Just as before, f is continuous. We have a new supposition. N is an even positive integer. Like before, delta x is defined in the same way. We divide the closed interval into n subintervals. We let each subinterval have the same length. And then Simpson's rule is the numerical approximation, s sub n. Delta x, notice that we're dividing by 3 in Simpson's rule. And then we have the curious situation that the left height and the rightmost height, left endpoint and right endpoint, appear with coefficient 1, but then counting by 2s, so the middle height is appearing with a coefficient 4, and then that's the middle, and then the right height appears once for the first pairing of 2 subintervals, but it appears a second time for the second pairing of 2 subintervals, so it picks up a coefficient of 2. And then f at x3 will be the middle height in the second pairing of two subintervals, and so it has a 4 on it. Right? So the thing to note is that now your coefficients will alternate 4, 2, 4, 2, beginning on a 4, alternating, and then always ending on a 4, as that is a middle height. So here is another method for numerical integration called Simpson's rule. And then those approximations in the limit will recover the true area. Very nice. That's Simpson's rule. And like before, Simpson's rule can be expressed out in terms of other rules. Simpson's rule, so remember that we want n to be a positive integer, a positive even, and even integers come in the form of 2n, or n being any counting number, and then with the index being 2n, that the value given by Simpson's is 2/3 of m sub n, not 2n, but m sub n, and 1/3 of the trapezoidal rule for n. Let's do a quick example of that. So in our example, we'll also go over calculating area. Before we write down the estimate for Simpson's, let's recall that we had these estimates for the midpoint rule and the trapezoidal rule, and that in these errors, the capital M was the maximum value of the second derivative. And then when we compute out capital M, we need a second order derivative, that the length of the interval is to the power 3, that's 1 bigger than 2, and that the n appears to the same count on the number of derivatives. All right, so that was for m sub n and t sub n. On the other hand, for s sub n, we now use not the second derivative, but the fourth derivative in computing capital M, and that the power on the length of the interval is 1 bigger than that. So 1 bigger than 4 is 5. And then the power on n in the denominator matches the derivative count on f. Okay. So in computing s sub 8, 8 is 2 times 4. In a previous assignment for this very definite integral, in a previous assignment, you computed m sub 4 and t sub 4. Go back and look at those values. Multiply them respectively by 2/3 and 1/3. Sum those quantities, and then that's a computation for s sub 8. Nice. And then something new. Use that assignment we just looked at as an example for computing s sub 4, Simpson's rule, n equal 4. For this definite integral, note the integrand is the derivative of arctan, and that arctan at 1 is pi over 4. Thus, s sub 4 can be used, if you multiply it by 4, can be used to come up with an approximation of pi, which is something very, very nice. Excellent. So you know that pi has an infinite decimal expansion, which does not have a repeating pattern, which makes it rather elusive. And yet Simpson's rule can provide you with an approximate value in a rather straightforward manner. Yet, appreciate that you don't get the exact value, you get an approximate value. So very simple concepts, but put into practice, you can then appreciate the value that these methods have. That's the end of the video. Thank you so much for watching. Please like if you find these useful. And I will see you on the next one.